joining us from.
Well, thank you for the invitation. Well, first I apologize because there are maybe a couple of people in the audience who have already listened to the talk. So the talk is about finiteness properties. Okay, so I will write down a question, and then I will give some context and give the definition you need to the question. And a bit later, I will state a theorem to answer completely the question. So I will consider lattices in PUM1. Open back lattices. So PUM1 is a group of holomorphic isometries of a complex hyperbolic space, M, or holomorphic automorphism of the unit ball of Cm as you want. So if I think of complex hyperbolic space, I just think of a set of negative line in a projective space of dimension m. Some dimension form like this. I consider this form 1c to the n+1, and I take negative line, and this is the same thing as the unit ball. And I will consider lattices, and I will need them to be arithmetic. It's really short at some point. I will explain you why. And I will also want them to have a positive first Betti number. So I will not talk about this, but these guys exist. It's only to catch them. Infinitely many commensurability classes. So I will talk about these objects. Okay. And the question is, take a generic morphism Z. And the question is, what are the finiteness properties of the curve?
And the what assumption of ability.
So I take a morphism onto Z.
What is it?
It's one of these guys. So it's a co-compact lattice here. It's arithmetic and it has positive first Betti number. And so,
yeah, is the B1 assumption always satisfied by passing to a finite index of group?
no, I mean, or at least it's not. So it depends on what arithmetic construction you start with. So the simplest example would be with the Hermitian form, it's conditional and property. This is Cash's theorem. And there are other, on the other side of the more complicated arithmetic constructions, it's not that U1 equals 0 for all convergent subgroup, and so if you have non-convergent. And there was in between there was a class in the way. So no, yeah. But there are examples. Okay. So we will answer completely the question up to replacing gamma by a finite index subgroup, maybe of large index. So maybe one thing you should have in mind is that for such a gamma, so this is a general statement about arithmetic groups, the virtual first Betti number is infinite, meaning this is what is this? It's the supremum of the first Betti number of finite index subgroup. So you should think that when we'll be taking a finite index subgroup where B1 is very large. And so the generic, what will be the meaning of generic? It will mean for the character should be in a dense open set. We'll find a dense open set which that any rational character in this set works. And the arithmeticity will show up at some point, but there is also many parts of the proof which apply just the complex geometry proof. So we can also build other example of hyperbolic groups with morphism of 2C, for which we can control the finiteness properties of the kernel. For instance, Stover and Toledo has built some closed scalar manifold of negative curvature, which is not locally symmetric. I mean, the construction uses all quotient because they are obtained by ramified curve, but what I want to say that, for instance, how also apply to this example of Stover Toledo. So we don't need all the time to have a symmetric space. It's really at one point. So you will see. Okay, so now I will define a finiteness property. Finiteness property. So there are plenty of finiteness properties in group theory. So the one I will talk about the topological one, the one. We say that the group G is of type FL, so L is some integer. If there is a CW complex, X such that well, X is a KG1, and the L skeleton of X is finite. So your space X will have infinitely many cells, but at least if you only look at cells of dimension up to L, there are only finitely many of them. Okay, so F1 is the same thing as finitely generated. If you have a finitely generated group, we can just take a wedge of finitely many circles and add the two cells to get relations, and then higher dimension cells to get something spherical. And F2 is the same thing as a finitely present. And so F3 is stronger, and K implies Fk minus 1. So starting with F3, all the groups are finitely presented, but we ask them to satisfy the stronger property. And let me just recall an important idea which will be a bit implicit in the work. So let's say that you have a group G, which is realized as pi1 of a CW complex Y. How do you build? Well, I'm cheating a little bit because normally to build a CW complex, you have to lose cells in the right order. But okay, let's forget about this. How do you build a KG1 from G? Well, if pi2 of Y is non-zero, you glue some three-dimensional cells to kill pi2. Maybe infinity, you will need to glue infinitely many. Then you get a space with the right pi1 and pi2 equals 0, and then you will glue four-dimensional cells to kill pi3 and so on. So you can build the KG1 from Y, adding three cells, four cells and so on. And if we know at the beginning that Y is a fundamental group item of 2G, and that a certain number of its higher homotopy groups are already 0, and we call the I as 0 up to K, from 2 to K. When the first homotopy group we need to kill is the one of degree K plus 1, so we start adding K plus 2 dimensional cells. So we build the KG1, adding cells of dimension K plus 2. So in particular, if Y was compact, we build a space whose K skeleton, whose K plus 1 skeleton is finite. Okay, so that will be a bit implicit. So There's another property, I will not write the definition, something called being of type F, and being of type F is having a finite perspective. So for instance, if you are pi 1 of a finite spherical complex, by definition you are type F, or pi 1 of a closed spherical manifold, you are type. So it is known that for all L, we define groups of the type and not F equals 1. Okay, so I just mentioned a few names, but there are really many works on this. So L equals 1 is related to coherence. So Reeves, for instance, gave the first example of hyperbolic groups which are non-coherent. I mean, there are many people who work on coherence, so there are many names. There's also a paper of Baumschlag and Rosblade, which shows that in a direct product of two non-abelian free groups, you have plenty of finitely generated non-finitely represented subgroups. For L equal 2, I think the first example of a group which is F2, so finitely represented but not F3, was given by Stallings. And arbitrary L, for arbitrary L, some example were built by Pierre. And okay, so I will just mention two more groups of cohorts also. They're also like related both like Deltin and Brady about finiteness properties of groups. I will maybe go back to it. And another which have worked on this kind of thing with Python or linear plots. And also, but it's more, I mean, that the techniques are really different from what I'm going to talk about. Example of simple groups, exotic finiteness properties. These are really, I mean, these are different techniques, so I don't know. I don't know these things well. So in all these examples, the groups which are F1, not F2, F2, not F3, they all appear as subgroups of direct products of free groups or surface group or combination of different type of factors. And here there are subgroups of right angular groups. And yeah, and it's more difficult to find example of groups like this inside hyperbolic groups. So let me first recall something about hyperbolic groups. So if B is hyperbolic, well, or K0, it works also. What I'm going to tell you. Even Fn for all n, and even type S is torsion free. Let's say that B is hyperbolic. How do you prove this? So you consider the K graph of T. And just look at the vertices and you do the Reeves complex. Okay, so you pick a large constant C and you build a simplicial complex for the vertices as the element of the group. And whenever you have n plus 1 element in the group which are pairwise at distance at mod C, you put n dimensional cell. And so this gives you a space on which the group acts co-compactly. And the theorem is that if the group is hyperbolic, this is aspherical. I mean, so this complex is aspherical, so you get a finite satisfying space. Okay, so how do you build things like this, starting with L equal to inside the hyperbolic groups? So it's more complicated because, I mean, the standard way to build a finitely represented subgroup in a hyperbolic group is to build something which is quasi-convex. And if you are quasi-convex, you will build yourself hyperbolic, so it will be a cell for all that. Okay, so standard way to build the finitely represented subgroup. Like quasi convex subgroups. And they are F1 for all of them. So you cannot do that if you want to find inside the hyperbolic group something which is found as F2 not F3. So let me recall a bit of history. So I think in Brady in 99, I think following an idea of Gromov and suggestion of Gromov, he gave an example of a G which is hyperbolic. And more fundamental Z, such that the kernel is finitely presented and not specific. And since then, for F2 non-F3 subgroups of hyperbolic groups, there were a few more examples built by Yashlolan, proponer. In 2000, I don't know, I think it's published in 2018 and 2021. So these are other examples with the same where the finiteness fails for the same dimension. And in the same paper, Brady asked whether you can have what happens for high limit. Take some integer L at least 3. And he asked whether you can have a subgroup of a hyperbolic group which is FL, not FL plus. We want a subgroup of a hyperbolic group which is FL, not FL plus. And so I think up to 2021, nothing happened on this question. I mean, the only thing that happened between 99 and 2021 were these two works, but I was still dealing with F2, not F3. And what happened in 2021? The first thing, which is not directly related to F5, not FL plus 1, but I will still mention it. It's a work of Italiano, Martelli, Migliorini. So Italiano, Martelli, Migliorini gave an example of a G hyperbolic. And then H, the group H, such that H looks like F. So it has a finite plus time space, but H is not hyperbolic. So this was also a big open question for the field of finiteness properties. Then I will not talk about this today, but with Claudio Iosa and Bruno Martelli, so we solved the n equals 3 case. We gave infinitely many pairwise non-isomorphic examples. We gave examples of hyperbolic groups. And subgroups. Sub H is F3 not F4. And these are also kernel of homomorphism. So why, I mean, there are plenty of other subgroups, but why can we say something about finiteness properties of the kernel of homomorphism related to Morse theory? You will see very soon. So I will not talk about this. And a bit later, so with Claudio, So we were able to answer this completely. So here is the theorem. So I will go back to my notation of gamma. So gamma is a lattice in the UN1. It's co-compact, and it has V1 positive. I don't write co-compact. And the claim is that there is a finite index subgroup such that for gamma naught and for anything else, anything deeper, so I could take any gamma 1 finite index in gamma 1. There is an open set, which is intense. Such that whenever you take a character in this open set, which is rational, or proportional to something rational, so the image should be a cyclic subgroup of R. Then the kernel is f n minus 1, not fn. Actually, if you like more algebraic finiteness property, it's not FPM. Okay, so in particular, we answer completely Brady's question. So we get for all m, we have plenty of examples. So you should really remember, and I'll try to explain this later on, that the degree, the dimension was a finiteness property phase. It's really the complex dimension, or half the real dimension. Okay, let me write another theorem. If you know about finiteness properties, I will maybe not define all the terms which appear. So I take the same gamma. So with the same hypothesis, what we prove is that the nth DNSF homotopical invariance of gamma is n. So just I will not define this thing, but I'll just say a word about it.
When all the theorems on the top board, the exotic subgroups are kernel. Also on the left.
Here, yeah.
Open there. So what is open was asking for?
No. It's a subset of it. Yeah.
But I mean, you could replace R by Z, right? It's like the integration.
Yeah, okay, but
Please tell us. It's a bit strange formulation.
okay, but I can tell you what the open set is. The way I think about it, it's a set of classes. So we are on a 2m dimensional real manifold. It's a set of classes that you can represent by a Morse1 form with only critical points at index n. So this is why I think about it like that.
Okay.
This is how I think about it. Okay, so well, I will not define this, guys. You know about it. If you don't know, we can chat about it afterwards. Okay, I will try to explain the proof of theorem. Did we start on time?
Like 5 minutes late.
Okay. Okay, so there are two things you have to prove. The lower bound, meaning that the kernel is not better than what it should be, so it's not FM. And this works, for that you don't need anything about the character, it's true for all characters. So upper bound, so depending on your taste or on how strong your result you want, you appeal to Milner or so actually, it's true for any homomorphism from such a gamma to even R that the kernel is never FPM. So there's a proof of that is equal to Betty numbers and the result by Luke. And I will only prove it for homomorphism to with values into Z using the result of Miller. So let's see. But you have yeah, but it's true for all homomorphisms. So okay. So what the argument I'm going to present, it's in an old paper of Milner called the infinite cyclic coverings. At the end, I think it talks about the Alexander polynomial and 3D topology, but the beginning is very general. So you take a manifold, a finite complex. You take morphism from Taiwan to Z, and you look at the corresponding cyclic cover. Okay? And what he does, so he writes down an exact sequence relating the homology of X hat and X, and it involves the action of the Beck transformation of the homology. And what he proves is that if the other characteristic of X is non-zero, then the homology of X hat is infinite dimensional for some difference. So yeah, it's not difficult, just some nice exact sequence. And one thing we observed, you already used this in that paper, with the Martelli, is that if X is a manifold of even dimension, using Poincare duality in all finite covers in between these two guys, you can show that the homology is infinite dimensional in some degree smaller than P. Okay, now if everything is, if X is spherical, then X hat is also spherical, it has the same universal cover as X. So X hat is a classifying space for X by 1, so it's a classifying space for the kernel. Here, I don't care about whether it has finitely or infinitely many cells, but one way to disprove, I didn't say it, but one way to disprove that the group is FL is to show that its homology in some degree lower than L is not finitely generated. So since that is the classifying space, this affirmation tells me that the kernel is not FP, and even not FP. Okay. The kernel is not space. And this is true for any homomorphism to Z, and if you want to, you can do it also for homomorphism with non-cyclic images. The different arguments. And this will apply in our context because the complex hyperbolic manifold, so portions of a complex hyperbolic space by a function Frico-combative, they have non-zero characteristics. So now I have to tell you how, okay, the other half, well, the lower bound, meaning why the kernel has a nice finiteness property.
Pierre, could you repeat what the stronger result of Luke is?
Take any homomorphism from pi1x to R. In general, the image is not Z, maybe it's Z.
Okay.
And he will, so if you have a morphism like this with a non-zero image, so it's something ZL, then the kernel it's not. Okay, so if you want something, the theorem of Luke is that you take any group and you take a surjection like this, and you have the kernel. what Luke proved is that you have something called L2 Betty numbers of a group, I think that's what it is. And he proves that if the L2 Betty numbers of the kernel are finite in some interval, and this is implied if the kernel is Fk, it implies it's finite. And then this implies that the L2 Betty numbers of the big group are zero in the same range. And okay, and so it's related to Zinger's conjecture. In general, let's say you have not spherical manifold, not always, but for pi one of a spherical manifold, the typical behavior of L2 Betty number is that they are always, well, it's a conjecture, they're always zero except in the middle dimension. So the Euler characteristic is -1 to the k. So vanishing Euler or non-vanishing Euler characteristic of the middle L2 Betty number is the same. So it's clearly related to this. So for complex hyperbolic quotient, we know that the middle dimensional L2 Betty number is non-zero, so the kernel cannot have all the L2 Betty number finite up to the middle dimension. But okay, if you only want to deal with cyclic image, the argument of Milnor is simple. Okay, so now, okay, I have X. Any manifold of even dimension, let's say aspherical. And I will introduce this thing that I mentioned before answering Emmanuel. So I will look inside H1. I will look at classes represented by a Morse form. All of whose critical point have index k. So actually, I should mention when we wrote a paper, we were thinking a lot about BNSR invariant. So everything is formulated in terms of BNSR invariant. But you can do all the proof of without mentioning the BNSR invariant, just because we'll never get out of this. We are going to add a comment. So if you think about it, and if you know BNSR invariant, you have this inclusion. And the whole proof, all the classes we really deal with, they are here. So this is an open set, so this is just more theory. And okay, first easy thing, classical. If you have a class in there, and which is rational, then the kernel is the kernel of the character is at k-1, so let me explain this. But this is and the next step will be how do you build manifolds where this open set is big. So okay, so you have a character, and you take the corresponding cyclic cover. That is the kernel. And here we do the same thing as what Besdin and Brady do, many other people do. So how do you study the topology of this covering space? So you have, let's think that the character is induced by a map from X to the circle, and on the cover you have a map from reals, which is so you have a map like this, which is Morse, and for any critical point, the index is k. Okay, so so this map is proper, so this is why we need the cyclic characters. Take a regular level set, it's a compact manifold, and what happens when you pass a critical value? So you know that if I look at the pre-image of this little interval, it will have the homotopy type of the fiber plus the k-dimensional cell attached. Okay. And if I take a larger interval, I know that it will have the homotopy type of the original fiber with a finite number of cells glued to it. So when you glue a k-dimensional cell, you kill a k-1 dimensional sphere, but you do not affect homotopy group up to degree k-2. Okay, so gluing a k sphere, a case this manifold does not affect I smaller than big minus smaller or equal. So at the end of the day, what you get is that if you are in dimension 4, so if k equal to 2, what you get is what they say is that this level is connected. And if you're in high dimension, what it says is that the pi1 of the level set is isomorphic to the pi1 of x hat. And the homotopy group has 0. Because they will have to be equal to the homotopy group of the entire space. Okay, so let's say that. So here you get that the kernel is finitely generated. And in general, you apply the remark that I said at the beginning. You will build a classifying space for the kernel starting from this compact manifold, and you only have to start killing by k-1. You have to start adding set of dimension k. So the group is fk minus. You get a classifying space, so you can rebuild a classifying space. From the fiber by adding cells of dimension. So it's fk minus. Okay. Okay, so now the end of the proof. So this is when some complex geometry will show up. So how to build a manifold of even dimension with this open set, which is big. So there are two steps. The first step is where the arithmetic speed shows up. It's a theorem of Libet-Sidieu. So this theorem, well, he used that for for what is called toroidal compactification of non-uniform lattices of U11, quotient. Okay, we use it for completely different thing, but it's a really useful theorem. I can tell you about the proof if you want afterward. Not difficult. So we take the quotient of complex hyperbolic space by our lattice as before, and maybe I need to make a small appendix to define something. So if you have a scalar manifold, scalar, you can always associate to it a complex torus, called it Salvan as a torus, and the holomorphic map. We have a map like this, I will call it A sub y, and the torus will be AY. It's a map which is holomorphic, then which is induces an isomorphism on H1. let's say with real condition. And it's built canonically from using Hodge. And what Philippe Essilio proved is that if you, so gamma is as in the beginning, so it's arithmetic. There is a finite unexpected group or finite cover of X if you wish. Such that the Albanese map of this cover is an immersion. And it's not difficult to see that once you have that this thing is an immersion, it will still be an immersion for any further finite cover. And so now, if you want more explanation about this later, I can tell you, but now I just explain the conclusion. And now for the conclusion, I will forget about locally symmetric space. And the only thing I will remember for the theorem is the following thing. So now consider y closed scalar with finite algorithm. So this means that you have a map from your complex manifold to the torus. And finite means that for any point in the torus, the pre-image of the point is finite. So in particular, it applies for an immersion. But now I really remember this. And this assumption we see that OK is okay, and why? What is basic observation? So imagine you have a complex Morse function or a complex Morse form. So if you have a Morse function like this, so the complex dimension is K. While the real part is the Morse function of the critical point of index. So if you don't like convex geometry, just remember that equation. This is what we use. So if I have now on a Keller manifold, so any class H1 Y is of the form the real part of alpha is alpha holomorphic one form. So if alpha looks like the differential of a function like this near its critical point, then I'm okay, I'm done. So, I mean, then this class is in okay. And actually, it's not difficult to see that if alpha has only finitely many zeros, the real part of alpha is also in the set okay, because you can morphify it. So the last claim I'm going to explain, I mean, there are two claims. So if the zero set of alpha is finite, then this lies in OK. So this is just multiplication if it's not already morphed. And the second claim is that in the space, so the map which takes alpha to the class of the real part of alpha, it gives you an isomorphism between your H1 and the space of holomorphic forms. And in the space of holomorphic forms, with having finitely many zeros, Athens. And why this is true? Okay, I will stop here. So you have this holomorphic map to a torus, and it's really built so that any holomorphic one formed here is the pullback of something with the torus. Okay, it's really a bijection between the holomorphic one formed here and here. And that hypothesis implies that if you take a beta here, which does not vanish when you restrict it to any positive dimensional subtorus, then its pullback will have finitely many zeros. We can explain later on. And this is the advanced condition. Beta does not vanish when restricted to a positive dimensional subtorus. Then alpha has finite many zeros. I mean, this is old. I mean, people have used this for many years. So it appears, for instance, in the paper of Simpson. I can explain later if you want. And so it's not difficult to see that this, imagine that, well, that has no reason to be true, but this is simple at the torus, or a product of finitely many simple vector I, then this is an open set condition. So only finitely many vector I. But in general, it's always it contains the J delta. So if you sum up all pieces, it gives a frequency of A. So I will stop here. Thank you.
Questions?
Yes.
Is it nevertheless true that there's always given such a lattice, there's always a finite index subgroup that projects onto Z with finitely different, but not finitely presented? Or is it necessarily? Or
In dimension 2, yes.
yes, but
I don't know.
is it?
No. Well, okay, is that there is a subgroup which is F1 not F2? Yes, because all these guys, they have the geometric submanifolds complex. The geometric manifold, or
if you want the Zariski density. Well, okay, Zariski density is the difficult, but I mean, you can take a free broad anyway. But okay, but is an example known in every dimension with this
F1 not F2?
with like a surjects onto Z with finitely generated, but not
No, I don't. No. So the curve you want the morphism to be defined on the big lattice. No?
yes, yeah.
Yes, so I don't know.
Great, so I think we have a question coming through in the chat that someone has their hand raised. You, virtual participants may also be able to unmute themselves, but you can type in the chat. Okay. Okay, that can work.
Is there some question in the chat?
There's someone with their hand raised, but they have not sent the question. So.
Lenny, do you hear us?
Maybe it's
Maybe it's a mistake.
yeah, it might be yes. All right. Great. So let's just thank the speaker one more time. And if you have other questions, you can discuss those. Okay. Next talk in 7 minutes.